Okay, hello. This is another theorem that you have surely never heard of or probably never cared to know about or think about, which can be proven with the Pigeonhole Principle, and it's hard to know how you would do it otherwise. This is the other big theorem that Gossett highlights. I did this proof in period 7 only on, I guess, the last day when we were back at Blair. Okay, let's go. Here it is. In any sequence of n squared plus 1 distinct numbers, there's a strictly monotone subsequence of length n plus 1. Okay, what's going on here? We have a sequence. So the you all know what a sequence is, so it's a certain list of numbers given in a particular order. I'm suddenly doubting myself that I have messed this up or something. Prove the sequence. Yeah, no, we're good. We're totally good. Yeah, the numbers don't, it doesn't need to be all the numbers. Yeah, it doesn't matter. Yeah, it's just going to be some numbers that are in some kind of, well, a sequence of numbers. These numbers are all distinct. So we have n squared plus 1 of them, and the numbers are all distinct. And now the claim is, so let me give an example, maybe already. An example of a sequence of n squared plus 1 distinct numbers. I think this is the exact, no, it's different. It's not the one given in the book. It's my own one that I came up with. I will write it kind of big across both boards like this. So 4, 0, 8, 3, 9, 1, 5, 7, 2, 6. Okay, so note that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 numbers. And so in my example, so I'll just make some notes on this example. I have, of course, set n equal to 3, and so n squared plus 1 is 10. In other words, I have a sequence of length 10. The reason why I paused for a second was I confused myself, but here I have chosen, in fact, the first 10 numbers from 0 to 9, but it doesn't really matter because the numbers come in some sort of order. So this applies to any 10 numbers because all that matters is their relative orders. So you might as well just pick the first 10, but okay. So if you have 10 objects, you might say, which are linearly ordered in such a way, and by that I mean there's always like a first one, a second one, a third one, and transitive property and all that kind of stuff. Also, the numbers are all distinct, so that's important. Then that's what we have here. Okay, finishing the theorem. What does the theorem actually say? It says there's a strictly monotone subsequence of length n plus 1. Okay, so first of all, monotone, monotonic, that's the same thing. Monotone, monotonic are words which refer to the fact that the sequence is increasing or decreasing. So of course, this sequence, the overall sequence, is not monotonic because 4, it goes down, then it goes up, then down, then up, then down, up, down, up, okay, so the general sequence is not monotonic, but what this theorem says is that it's possible to select a subsequence which is monotonic. And okay, what is a subsequence? It's possible that this is your first time ever hearing the phrase subsequence. A subsequence is given a particular sequence, a subsequence of that sequence is just another sequence in which you select only some of the elements of that sequence. But you don't change the order. So an example of a subsequence would be, 0, 3, 9, 5, 7. That would be considered a subsequence of, let's see how well this red comes out. Yeah, that's fine. This sequence 0, 3, 9, 5, 7 would be considered a subsequence of my original sequence here. Okay, so what this says is that there is a subsequence of length n plus 1. And so for our toy example here, what this is saying is that if you give me a sequence of length 10, then no matter what that sequence of length 10 is, it is possible to come up with a subsequence of length 4, which is either increasing or decreasing. So that's what monotonic means. Monotonically increasing or monotonically decreasing. In this case, strictly here is just totally redundant. When people say strictly monotonic, they mean actually increasing or actually decreasing as opposed to staying the same. But it's, in here they can't stay the same because we've already started with distinct numbers. But sometimes in some contexts if people leave off strictly, then they just mean non-decreasing. So getting bigger or staying the same. Okay, so that was all the vocab. Why? And okay, to put a little bit of colorful language into this, to make this seem like something you might care about, what this kind of says is, suppose you have some data, and the data, you have 10 bits of data. What this means is that you can cherry pick your data, no matter what the data is, totally just some crap data, maybe possibly signifying nothing, with a bunch of just random numbers. As long as those numbers are all distinct, you can, deviously, you might say, choose to highlight some of the numbers in the sequence and ignore other ones, such that you're not changing the data, but you are constructing the data so that you're showing that the numbers are going up or going down. In other words, suppose what the hell? This is now so dumb. Suppose on the first day I eat 4 cookies, and on the second day I eat 0 cookies, and on the third day I eat 8 cookies, etc., etc. Well, this is a pretty just random different numbers of freaking cookies I ate every day. But if you wanted to show that I am what this says is that by selecting my cookie facts on only certain days, I can tell a narrative that I'm eating more and more cookies, or fewer and fewer cookies. So perhaps we should just do that right now. What is the subsequence of length 4, which shows that this theorem is true in this case? I need 4 numbers which all go up or down. I think there are, in fact, a lot of them. If you take 0, 1, 5, 7, for example. That is a subsequence of length 4, which is monotonically increasing. And if you just took those 4 numbers, then you could tell a narrative that my cookie consumption is going up. Alternatively, you could pick 0. Maybe that's the only option. 0, 1, 2, 6. That shows that my cookie consumption is going up. Is there one you could use to show that my cookie consumption is going down? No, not of length 4. Okay. Alright, so why must there be this subsequence of length 4? And of course, I want this proof to be general enough to refer to any sequence of length 10, not just this particular sequence. And also not even sequences just of length 10, but any sequences of length n squared plus 1. Okay, so what I want to do is, what I need now is some sort of systematic way of finding all possible subsequences which are monotonically increasing and monotonically decreasing. And so let's introduce a little bit of notation. Now, what I want to do is, I want to construct ordered pairs. Construct ordered pairs of the form, I sub j and d sub j for each element in the sequence. For each j, where j is going from 1 to n squared plus 1. So for every single one of finding all kinds of tiny mistakes in my notes as I go. Let me just fix that. And 1 second. There's some other mistake from half an hour ago. I forget. Whatever. Okay. Good. Back on track. So what is this ordered pair? This ordered pair associates with every single one of the associates to every single one of the n squared plus 1 elements in my sequence. Two numbers. The length of the longest increasing subsequence starting with that number, and the length of the longest decreasing subsequence starting with that number. I'll write that down. I'm going to squeeze it into this little spot. Let I sub j be the length of the longest increasing subsequence starting with j, starting with x sub j, where x sub j refers to the element in the jth spot. So have I done this right? Yeah, I think this notation is good, right? J is the index of the element in my sequence. So here I have 10 numbers. So here j is 1, 2, 3, all the way up to n plus 1. And x, let's use x sub j to refer to the element in the jth position in the sequence. And I sub j is the length of the longest increasing subsequence starting with x sub j. Let's just do that first. Let's see, we'll use red and purple. So what I'm now going to do is, also people may notice a baby crying in the background, and that's because there's a baby crying in the background. And that's because I'm recording this video during nap time. So, let's go. What is I sub 1? Or even more casually, let's just sort of do it. I'll do it in red. So what is the length of the longest increasing subsequence starting with 4? Okay, well, surely there's sort of just an algorithm for this because these numbers are all finite, but because these numbers are small enough, we can just do it in our heads. Hopefully I don't screw this up, that would be embarrassing. What's the length of the longest subsequence starting with 4? Well, I can do 4, 8, 9, so that's 3. I can do 4, 5, 7, and I can do 4, 5, 6. So I claim that the longest subsequence, the longest increasing subsequence starting with 4 is 3, because, and there are 3 of them. 4, 8, 9, 4, 5, 7, and 4, 5, 6. All right, hopefully I didn't screw that up. How about 0? What's the length of the longest increasing subsequence starting with 0? Well, here there's going to be a lot. Let's see. 0, 3, 5, 7. That's one of length 4. 0, 3, 5, 7. There's also 0, 3, 5, 6. And there are many other subsequences which are shorter, but there is certainly one of length 4. And I don't think there's one I don't think there's a subsequence that's longer than 4. I think I would notice that. 0, 3, 5, 7, 0, 3, 5, 6, 0, 1, 2, 6. That's another one. 0, 1. Yeah. So there are several of them of length 4. Okay, we continue. How about 8? Well, the only one that's going to be increasing from 8 is 8, 9. So the longest subsequence starting with 8 is 2. Okay, this gets a little bit easier as the sequence gets shorter. How about with 3? Let's see, I can do 3, 5, 7 or 3, 5, 6. So that's a subsequence of length 3. How about with 9? Well, 9 is the largest number in the sequence, so the only increasing subsequence will be the subsequence of length 1. Which consists of just 9 itself. How about over here? 1, I guess I can do 1, 5, 7, 1, 5, 6, 1, 2, 6. But anyway, the longest one will be 3. And 5, I can do 5, 2, 6. That's of length 3. Once I get to 7, there are no subsequences starting with 7 that are increasing except the trivial one that has just 7 in it. So the longest one has length 1. And here 2, and here 1. Okay. Never mind why I'm doing this, but I think that makes sense. And now I'm going to squeeze this in here. Let d sub j, so here the I stands for increasing, d sub j be the length of the longest. And now I will stop writing decreasing subsequence starting with x sub j. I ran out of space. Now we just do the whole thing over again. After all, we were looking both for increasing subsequences of length n plus 1 and decreasing subsequences of length n plus 1. Monotonic includes both of those. Okay, starting with 4, now I'm looking for ways to go down from 4. So let's see, I can do 4, 3, 1. I can do 4, 3, 2. And I don't think I can do anything better than that. Nope. 4, 3, 1, 4, 3, 2. And so the length of the longest decreasing subsequence starting with 4 is 3. Here, 0 is the smallest number, so the only subsequence that's decreasing starting with 0 is just going to be the trivial one. Here from 8, let's see, we can do 8, 3, 1, 8, 3, 2, 8, 7, 6. Anyway, all of them have length 3. Hopefully I didn't miss any. From 3, we can only do 3, 1 or 3, 2. So that's 2. From 9, we can do, let's see, 9, 1, 9, 2, 9, 7, 6. So there is a subsequence of length 3 starting with 9 that's decreasing. From 1, there are no smaller numbers left. 5, 2, 7, 6, 2, and then boom. Okay. So, I have now, sort of tediously, and just for my example, constructed these ordered pairs. What is the significance of these ordered pairs? Well, they help us visualize what's going on because now, returning to the statement in the theorem says that there just must exist, it's a pure existence statement, this theorem, some subsequence of length n plus 1. Well, in my example, where n is 3 and the length of the sequence is n squared plus 1 equals 10, then all this theorem is asserting is that there is a subsequence of length 4. And you will, I hesitate to call it an algorithm, but it is kind of an algorithm in a certain way. You could have coded this very easily with just a whole bunch of loops and stuff, or something more sophisticated. What the theorem says is that there must be a subsequence of length 4. And indeed, by tagging every element in this sequence with this ordered pair, we see that a 4 does appear. And so, in fact, a way to rephrase the theorem is that a 4 must appear somewhere among the elements of all these ordered pairs. and indeed a 4 does appear. And so the subsequence guaranteed by this theorem is, well, we actually saw when we just did it out using common sense, that there are several subsequences which satisfy the theorem for this example, but they all start with 0, right? And the 4 of them are, I guess, all increasing subsequences starting with 0. So 0, 1, 5, 6, 0, 1, 5, 7, 0, 3, 5, 6, and 0, 3, 5, 7 are the 4 subsequences starting that are increasing that start with 0. But anyway, the presence of this 4 here should make me very happy because that's what's being guaranteed, that there is a subsequence of length 4, it starts with 0. Okay, so now conversely, if I'm trying to prove this theorem, well, I'm definitely going to do this proof by contradiction because it's sort of a pure existence statement. If I'm doing this proof by contradiction, then what I need to do is somehow show that this 4 doesn't appear. Okay, so now I'm doing kind of a hybrid approach here where I'm using the example to explain things, but I'm claiming that my logic applies to a more general case, or, well, I guess I'm doing the proof, but I'm using this example as a guide. Having constructed this ordered pair for every single element, I now I now prove a little lemma. So my lemma says, lemma, there is an I sub j or a d sub j. This is really not a lemma. Hold on one second. Well, okay, it's not a lemma. This is just the theorem. So I'll just say claim. A little bit confusing way of putting it. No, this is fine. Claim there is an I sub j or a d sub j, which is greater than or equal to n plus 1. And that just proves the theorem. So thus proving the theorem. And because the theorem says that there has to be an increasing or decreasing subsequence of length n plus 1, and we've rephrased that as either that the number n plus 1 or a larger number appears somewhere in these set of ordered pairs. Okay, but why? Why? Certainly in this case, the 4 just popped up, but why must there be a 4, you might have asked? Prior to filling in these red and purple numbers, you might have wondered, how would I know that a 4 would appear, or perhaps a larger number? Well, what does it mean for the number 4 to not appear? If 4 somehow didn't appear among my purple and red numbers, nor any number larger than 4, then it would mean that all of these numbers were in fact 3 or less. So if not, then each of the I sub j and d sub j is in fact less than or equal to n, in this case less than or equal to 3. And that is, however, impossible. Note that, of course, that each of the I sub j and d sub j have to be, this is a j and that's a comma, each of them have to be greater than or equal to 1, because for any number there's always a subsequence of length 1, including just itself, and the longest they can possibly be is n plus 1. Why is that? N. Because... What? Oh, yeah, that's... sorry. Sorry. This is the conclusion of this assumption I've just made, right? I'm claiming that this 4 or larger number must appear. There must appear a number greater than or equal to n plus 1. So suppose not. If not, then every single one of these numbers is in fact less than n. Well, that can't be because gotta just get my thoughts here together. Oh, because okay. So it's not clear why that can't be. But I will first establish a certain fact, which is that if this 4 isn't here, and in fact that number is something less than or equal to 3, then there aren't enough numbers to go around, and some ordered pair must repeat, right? So since I sub j is guaranteed to be between 1 and n, and d sub j is guaranteed to be between 1 and n, that's what I just kind of noted over here, sort of repeating myself, then there are only n possible values for the left element, for the red numbers, and there are only n possible values for the purple numbers. Then there are only n squared possible distinct ordered pairs. Distinct ordered pairs. By the pigeonhole principle, 2 of the n squared plus 1 ordered pairs are the same. In other words, on the assumption that this theorem is false and that this number 4 doesn't appear, then all of the numbers and all of these ordered pairs have to be either 1, 2, or 3. But if there are, if all the purple and red numbers are just 1, 2, or 3, then there are only 9 possible different kinds of ordered pairs, and yet we have 10 numbers in our sequence. And sort of more generally, there are n squared possible ordered pairs and n squared plus 1 terms in my sequence, and so 2 of them must be the same. So this is the key moment at which we applied the pigeonhole principle, and we applied it simply to establish that there's an ordered pair that repeats. Why is that so? Why is that fact that the ordered pair repeats so helpful? Well, if the ordered pair repeats, what we can now say, and I've run out of space, so I'm just going to talk out the rest of this proof. What I now know is that somewhere on my list of ordered pairs, there's an ordered pair at the jth spot, I sub j comma d sub j, and it has to equal I sub k comma d sub k. For some, so this is going to be true for some j and k between 1 and n plus 1. Okay. More casually, what this is just saying is, dude, if you construct these red and purple numbers next to every single element, then there's some ordered pair which repeats. So somewhere it says like 3, 2, and then again says 3, 2. Why is that so disastrous? Why is that such a problem for an ordered pair to repeat its position like that? Well, what's sort of the big deal, so to speak, if an ordered pair repeats? Okay, well, just to clarify this a little bit, without loss of generality, let j be less than k. I mean, that's just so we can talk about j being less than k. And now also note that, of course, that x sub j is not x sub k, because built into the theorem is that these numbers are all distinct. Okay, so what we really have are 2 numbers in my sequence. This is a very long-winded way of saying. I have 2 numbers in my original sequence, in this case it's 3 and 5, such that such that the numbers are different, and yet they have the same ordered pair associated with them. Okay, well, there are just two cases to consider. Whether x sub j is less than x sub k, or x sub k is less than x sub j. And both of these are going to lead to a contradiction. And here is kind of the idea. The idea is, if you have these two numbers that both have the same ordered pair associated, well, what does that really mean? It means that when you're right here, what this is saying is, let's look at the red numbers first. Yeah, what the red numbers are saying is that the longest increasing subsequence starting here is of length 3. But this says that, I'm now kind of confusing myself. 5, is this just wrong? This had to just be wrong. Oh, geez. This is just not a 3. This is a 2. 5, 7. 5, 6. Wow. Okay, so I have to do a different one. I have to do... 1 second. Where is my... Oh, well, here it just wouldn't happen. Okay, I'm trying to illustrate a proof by contradiction, but using an example, which doesn't work. Okay, so we can't. Well, I think I can erase this example now, and I will replace my toy example with a generic example, which is of course false, because we are in the middle of a proof by contradiction after all. And so I have like some number, let's call it x1, then I have some number x2, and then I'm continuing on, and I have somewhere I have this number xj. Yeah, this is the way to do it. And then later on I have this number xk, and finally I get to the last number in my sequence, which is n plus 1. And what I have done is I have already gone through and associated with every single one of these numbers an ordered pair. And the thing that happened, which is impossible, is that I got two different numbers in my sequence with the same ordered pair associated with them. And so here I have this number I sub j and this number I sub k, and they're the same. So I'll just write in, let's see, here I will write I sub j, and here I'll write I sub k. But the idea is that these are in fact just the same number. In fact, maybe I'll just call it I, because it's just the length of the longest increasing subsequence starting with those numbers is in fact the same number. This is what I want to show is impossible. And, then